I am SK Das, Director, National Water Academy. Very good morning to today's speaker, Shri N. Rai sir, Chief Engineer, Central Water Commission, and all the participating officers who have joined this webinar series today. Just to inform you that this webinar was to be concluded on on 11th, means in the last topic had been covered, that is hydromechanical review of these dams. But we have included 3 more topics, and out of those 3 topics, today's topic is very important. That is means case studies related to hydrological review of dams with and other topics we have included in this webinar series. The early warning system to be delivered, early warning system for hydro projects, which is to be delivered on 25th February. And further that means on 4th March, that is hazard classification of dams will be delivered, and then we will conclude on 4th March this complete webinar series. We have already, means Rai sir has already delivered one session on this hydrological review of dams. But on the demand and request from the participants side, we have requested him again to come with some case studies, and I'm very thankful to Rai sir that means he has given his time. Apart from being his busy schedule, he spared the time to deliver this session. So before the start of this session, I'll just briefly go through the resume of the Rai sir. Very briefly, I'm going through it. All we know, he is an eminent officer, means expert of hydrology in India, we can say. He is officer of Central Water Commission. He has graduated from this Kamala Nehru Institute of Technology, and after that he has done his master degree in hydrology from Roorkee. He is Central Water Engineering Services Group officers and joined Central Water Commission in 1995 through UPSC, and he joined as assistant director and worked there in the field of hydrological and hydrodynamic modeling. He received the Merit Award of Central Water Commission for developing the mathematical model for cascade development of Chambal River, and contributed 4 technical papers in various national and international conferences. Friends, just I am going very briefly, otherwise I know his work. Everybody knows his work. He has presented so many technical papers, and he has contributed in hundreds of projects, in either in DPR stage or in PFR stage, or in many times review of hydrology is being done after construction also in the projects. So I'm going very briefly here. He is presently Chief Engineer in MTBO, Central Water Commission, Gandhinagar, and he has carried out the hydrological and hydrodynamic modeling for more than 35 river valley projects for design flood estimation, dam break studies, glacial lake outburst flood studies, backwater studies, reservoir sedimentation profile studies, surge analysis, reservoir and channel routing studies. He evolved the methodology for glacial lake outburst flood estimation. He has also authored around more than 20 technical papers in the field of hydrodynamic and hydrological modeling. So this hydrodynamic and hydrological modeling having a good, very good expertise in this domain. I remember many projects here. Earlier, he was involved in Parechu Lake out west when it happened, in Kerala flood yesterday. I'm not naming projects here. Just I'll invite sir to deliver further. So, sir, welcome, sir, in this 16th topic of this webinar series, and I welcome you and kindly deliver the session.
Thank you, Dasab. I think this is the second webinar on design flood. In first webinar, also I covered one case study of Sardar Sarovar project. But in this webinar, we will discuss about how we are selecting the storms, how we are applying different correction factors. So these things we will discuss in detail, and then again one case study I will show you. And after webinar, I think in the last webinar also there were a lot of doubt to the people. So if I think around 45 or 30 minutes we will give time for discussion. So whatever queries are there, I will try to answer all those queries. So I'm going to share my presentation now. Share. Presentation is visible to everybody?
Yes, sir. Yes, sir. Visible, sir.
Okay. So basically, I am covering in design flood review. We can go for flood frequency analysis also, but in most of the cases, for standard project flood and probable maximum flood, we are going for hydrometeorological approach only. So I will discuss this hydrometeorological approach, and as far as flood is this flood frequency approach, so that is quite easy. Only you should have the annual flood peak data, and then using that flood peak data, you can estimate the desired return period flood, like 100-year, 500-year also. Generally, PMF, we don't consider using flood frequency analysis because the PMF return period is assumed of the order of 1 in 10,000. So strictly speaking, flood frequency and hydrometeorological approach, we cannot say that the PMF return period is 10,000 year only. It may be even 1 lakh year. A lot of works has been done by different researchers. So to specify what is the return period of the PMF, so there is no specific rule or there is no specific saying that this is 10,000 year, but it is assumed it may be of 10,000 year. What is hydrometeorological approach? In hydrometeorological approach, our main attempt is to analyze the causative factor responsible for production of severe floods. So this causes, what could be the causative factor? The causative factor shall be your basically rainfall. So that is one of the aspect. Then design flood, basically when we are going for estimation of the design flood, so we should have design storm hydrograph. Once you have selected your storm and you have carried out all those analyses, like you have transposed that storm, you have calculated what is the depth in different subcatchments. After that, you have to prepare the hydrograph also, and for that you shall be requiring the hourly distribution coefficient of the rainfall. So using that and then assuming the loss rate, you can compute the what is the will be your effective rainfall hydrograph. So that is required. Then another important aspect is derivation of the catchment response function, that is the unit hydrograph. So unit hydrograph, there are the different methods for estimation of the unit hydrograph that we will discuss. The catchment response function can be either a lumped system model or a distributed lumped system model. This is important. Lumped system model means we are considering the entire catchment as a single unit only. But in distributed lump system model, we are making a number of sub-catchments for the project catchment. So in that case, when the catchment area and why when we are going for lump system model, why we are going for the lump system model? If the catchment area is small, say 500 square kilometer, 1000 square kilometer, up to even up to 5000 square kilometer, you can consider the lump system model, depending upon the what is the equivalent stream slope and catchment characteristics we can decide. But up to normally 2000, 3000, up to 3000 square kilometer, we can go for the lump system model. But if the catchment area is large, say 20,000 square kilometer, 50,000 square kilometer, 50,000 square kilometer, in that case, we cannot go for the lump system model. In that case, we have to go for the distributed lump system model, where we will make a number of sub-catchments out of the catchment area of the project catchment. In lump system model, the unit hydrograph is assumed to represent the entire catchment area because your single catchment you are considering. In distributed system model, the catchment is divided into smaller sub-catchment and the unit hydrograph of each sub-catchment is worked out. And once you have got the unit hydrograph and this storm hydrograph for each sub-catchment, then you will get for each sub-catchment, at each sub-catchment outlet, you will get the flood hydrograph, and that flood hydrograph, depending upon the distance of the other projects in your project catchment, you have to go for reservoir routing and channel routing, etc. Here I would like to mention you ki whenever we are estimating the design flood like PMF or SPF, then this channel routing in the distributed system lumped model, we go for the channel routing, but the reservoir routing should be strictly done if upstream project is having dedicated flood cushion. If the dedicated flood cushion is not there in the upstream project, then while estimating the design flood of any downstream project or probable maximum flood or SPF, no reservoir routing should be carried out because we are trying to estimate the severe most condition, and reservoir routing should only be carried out if the upstream project is having dedicated flood cushion, not the dynamic flood cushion. Dynamic flood cushion means you are operating the reservoir at lower level at particular period of time, and then if the flood is coming, then you can go depending upon the rule curve up to certain level, but that is the dynamic flood cushion. Dedicated flood cushion means in a particular month you are keeping your reservoir at that level only, unless 10 meter or 15 meter you are always having that space for the flood control. So that is the dedicated flood cushion. So because in previous lecture also a number of people have asked me this question whether we should go for the reservoir routing. So reservoir routing you should go only if the upstream project is having dedicated flood cushion. If there is no dedicated flood cushion, then the no reservoir routing should be carried out while estimating the design flood of the downstream project. The main advantage of hydrometeorological approach is that it gives a complete flood hydrograph. Okay, so because only estimation of flood is not the only requirement. Once we have estimated the flood for the existing project, suppose your design of your flood has increased, say by 10% or 15%, then while considering the most critical condition, you have to route that flood through that project. Then you will see how much water level, reservoir level is attained, whether adequate freeboard is available in spite of increase in the design flood, because suppose your normal freeboard is 1.5 meter. For existing project, if the other conditions satisfied, then in the case of probable maximum flood or severe most flood, we can consider even 1.2 meter or 1 meter freeboard is available. Then that could be hydrologically safe, provided that you carry out that stability analysis also, all those things with the help of designer. If everything is okay, stresses are in the normal level, then there is no problem in that. So for existing projects, that our own project, that can be considered like that. So for reservoir routing, we need complete flood hydrograph, because in that only the volume will be there. But if you are using, say, flood frequency analysis, so there you are going to get only one peak, and with the help of one peak, you cannot know what will be the volume associated at different period of time. So that is the beauty of hydrometeorological approach. You are getting the complete flood hydrograph, and with flood hydrograph associated volume also you are getting that. And this allows making a realistic determination of its moderating effect while passing through a reservoir or a river reach. Now, as already I told, when you are going for the design flood using hydrometeorological approach, then the storm study is one of the most important component of design flood analysis. So, for storm study, what is required? Daily rainfall records of all rain gauge stations in and around the region under study. Then rainfall data of self-regarding rain gauges and data of storm dew point and maximum dew point temperature. So this is a very Herculean task. A lot of time is required. So just to save that file, that time, Central Water Commission in association with the IMD and even IMD alone also have published the probable maximum precipitation PMP atlases. In those PMP atlases, how it has been formulated. So for making those PMP atlases, data right from 1906 up to say year 2014-15, whenever that study started, and it is also PMP atlases are being revised after every 10 or 15 years. So by that time, whatever the storm records, all the storm records are collected, analyzed, and in that first it starts from rainfall data only. Based on the rainfall data, storm iso heights are prepared. So for most of the severe storms, storm iso heights has already been prepared by the IMD, and those has been incorporated in the PMP atlas. Suppose a new storm has occurred, which is the severe, very severe storm. So for that storm also, while preparing the PMP atlas, if all the rain gauge data are available, then the ISO heights can be generated nowadays very easily using the GIS techniques. So rainfall data of self-regarding rain gauges, this is very important. Because you see, now you must have observed in the last few years, what we have also seen, the intensity of the rainfall is changing. Intensity of the rainfall has increased at number of places. So if you are having the self-regarding rain gauge data, so analyzing that data, you shall be able to gauge the present situation of the intensity and present situation of the distribution, time distribution coefficient. Suppose you are using some 20 years old data. So at that time, okay, rainfall may be 30 years old, 50 years old, storm is so high. But suppose if the same storm is going to occur in the catchment now, then whether that time distribution coefficient of 30 years old shall be valid, perhaps it may not be. So for that, if you have used the self-regarding rain gauge data of latest 5 or 10 years, so that is representing the present trend of the distribution of rainfall, hourly distribution of the rainfall. So by that way, you are also accounting for the climate change effect in your design flood estimation. This is very important thing, because most of the people don't realize. People will tell, no, now what will be the impact of the climate change? How in your design flood study? If I have used the latest data of self-regarding rain gauges, then indirectly I have already accounted for the climate change effect impact in my design flood estimation. That is my answer. With data of storm dew point, yes, that is very important in the climate change. What is that possibility? temperature is going to rise. Okay. If the temperature is going to rise, your dew point temperature is also going to change. Okay. Then maximum dew point temperature also, suppose at some location, maximum dew point temperature was corresponding to year say 1988, and it was something around say 31 degrees centigrade. But now you have analyzed, we have prepared or revised our PMP atlases in year 2014-15. So up to year 2012-13, whatever the dew point temperature data was there, that data has been taken. Okay, and using that dew point temperature data at a particular location, earlier it might have been 32 degrees centigrade, yeah, 30 degrees centigrade. Now we are getting the maximum dew point temperature 32 degrees centigrade. So again, in this process, we are indirectly accounting for the impact of climate change. I think that is pretty clear to everybody how we are accounting for the climate change impact in our design flood estimation. So through rainfall data of self-recording rain gauges and data of storm dew point, we are indirectly accounting the impact of climate change in design flood estimation. Now, another important aspect, what should be, because a number of people get confused whether I should consider 24-hour storm, 1-day storm, or 2-day storm, or 3-day storm. So, okay, so its answer lies in the unit hydrograph. For all practical purposes, the unit hydrograph base governs the duration of storm depth. Okay. For unit hydrograph having a base of 24 hours or less, then your 1-day storm shall be sufficient. Up to say, normally we consider TP also, time to peak of the unit hydrograph is also one of the criteria. Suppose your time to peak is say 14 hours, okay, and your base is suppose 28 or 29 hours, okay, or 30 hours. So 10%, say 14 hours, so 14%, 10% of the 14, 1.4, the total will be 15.4. So any storm having the duration of 16 hours and more, that will suffice your requirement. Okay, so in that case, your 24-hour storm or 1-day storm shall be sufficient. In the case of UG base is more than 24 and less than 48. So normally we consider like that, but even up to 32 hours, you can like, and you should consider 1.1 TP also, but it is says 46 hours or 40 hours. Then you have to consider your time base of the unit hydrograph is say 40 hours. Then you have to consider 2-day design storm. For bases having the UG base of more than 48 hours, a design storm of 3 days should be considered. And normally in Indian condition, for more than 3 days storm, ISO heights are not prepared. So maximum 3-day storm shall suffice for any type of catchment. So storms of period exceeding 72 hours are not generally required to be considered in the design flood estimation. Now, how we are estimating the probable maximum storm or SPS, standard project storm? The most common method of estimating probable maximum storm for a project basin is one involving the transposition of selected major storms to the project basin and its maximization there. So, and this statement doesn't mean ki only in the project catchment that storm should have occurred. No, there are the criteria for storm selection. Like in the plain area, I will just show you which storm can be considered for transposition into the project catchment. So the 3 main steps of transposition and maximization of the storm is selection and analysis of past major storms on record considered transposable to the project basin. First, remember this thing. This is very important. You have to select all those major storms which can be transposed in that project basin, and what is the criteria of transposition, that will be discussed. Then adjustment of these transposed storms for maximum moisture that could occur over the project basin. That is another, that is called the maximization technique. How much, if the say dew point temperature would have attained corresponding to the historical one, then how much extra rainfall could have taken place. That is called the maximization of the transposed storm. Then envelopment of the transposed adjusted storms. So these are the three main steps for estimating the probable maximum storm or standard project storm. Now, what is the criteria for storm transposition? So storm transposition means application of a storm from one area, sorry for my spelling mistake, one area to another area within the same meteorologically homogeneous region. So that is important. Like, you cannot consider the Eastern Ghat storm into Western Ghat. You cannot consider Western Ghat storm into, say, Eastern Ghat. You cannot take it like that. So it should be meteorologically homogeneous. Okay, like Ganga Basin storm, we cannot put in the Brahmaputra Basin. Brahmaputra Basin storm, we cannot bring into the Ganga Basin like that. So that should be meteorologically homogeneous region. The orientation of storms should not be adjusted by more than 20 degrees. For every storm, seeing the ISO height, you shall be able to know its orientation. So while maximizing the storm in the project catchment, we can rotate the entire isohydral system, but that rotation should not be more than 20 degrees. That is one of the criteria, and this criteria has been formulated by WMO. Okay, so everybody is following this criteria. The transposition should not be attempted if it involves crossing a barrier or change in elevation of 100 meters. Okay. If there is a barrier which elevation is more than the elevation difference, not elevation, elevation difference is more than 800 meters, then from one location to another location, you cannot transpose that storm if barrier height difference is more than 800 meters. That storm will not be transposed. No storm should be transposed in general beyond 2 degree latitude or longitude from the place of its occurrence. That is also one of the criteria, because most of the storm, like in Indian condition, storms, most of the storms generated from the Bay of Bengal, but in the Western Ghat, in Kerala and part of the Western Ghat, Maharashtra, you will get the severe most storm occurring from the Arabian Sea, but around 80% area of the 85% area of the India is being covered from the storm originated from the Bay of Bengal, and these storms having a particular track. So that track has been analyzed by the IMD and Incentive Water Commission also. So considering those tracks, these criteria like 2 degree, that is applicable for many of the storms. It should not, it will not deviate by more than 2 degrees from its track. So that's why this 2 degree latitude longitude criteria has been given, but this is for the plain or rolling type of terrain. This criteria is not applicable for the hilly terrain where the precipitation is of orographic nature. Now, what is the another criteria for storm selection? The area of transposition is considered at 2 degree by 2 degree longitude for nearly flat region, and 0.5 degree by 0.5 degree to 1 degree by 1 degree in a mountainous region. This is as per para 5.2.2.1.1 of WMO manual of 1986. So this criteria has been evolved by WMO, and this is being followed by most of the country. Coastal storms, storms having centered west of the Western Ghat and east of Eastern Ghat, were not transposed to the catchment located far inland. This is very important. Suppose some storm has occurred in Kerala, okay, so you cannot transpose that storm into Tamil Nadu, like there is a barrier. That barrier height is more than say 6,000 feet. So number one, barrier is there, so you cannot transport. You cannot transport that storm saying by way basin. That is not. And that is a coastal storm. What is occurring in Kerala? But that storm can be transposed along the coast. Further, suppose barrier is not there, then also like Dakor storm occurred near Gujarat. Okay, can I transport that say 150 kilometer inward? No, that should be avoided. Normally up to 50 or 100 kilometer you can go from the coast. Beyond that, that storm should not be transported. Because why? Because here near the coastal storm is having the different meteorological conditions. So you should not go transport those storm for inland. Transposition to catchment larger than 50,000 square kilometer may result in unrealistically excessive PMP estimate. As per WMO manual, this may result in a severe unrealistic situation of flooding that is not experienced by the catchment. So this statement, this is given in the WMO manual itself. It means whenever you are considering transposition of a storm in a very large catchment, having catchment area more than 50,000 square kilometer, then you have to take due care for the selection of the storm and its transposition and computation of all the correction factors. Now, how are we going to select the storm and how we are going to calculate different adjustment factor? So that we are going to discuss this slide. So what is the step? First step is select the transposable storm with maximum rainfall depth and having aerial extent to cover the entire catchment. So suppose you have got 5 storms. Okay, one storm has given the maximum say 1 day storm of 300 millimeter, another has given 350, another has given say 400 millimeter. Okay, but while you have seen this 400 millimeter rainfall and seeing is its ISO height, you are seeing, suppose your catchment area is 20,000 square kilometer, but the outer isoheital extent of say 400 millimeter maximum depth recorded rainfall, it say suppose catchment area is 20, but its aerial extent is say 16,000 square kilometer. Then we will not consider that 400 millimeter maximum depth storm. Then we will see 350 millimeter rainfall, and then again we will check whether it is covering the entire catchment. If it is covering the entire catchment, then I will go for 350 millimeter rainfall. And because in that case 400 millimeter storm, if we have selected, the overall catchment representative depth of that storm, you can try also, that will be less than the what you are getting using the rainfall, for which the maximum recorded depth near the eye was 350 millimeter. So that is the, so both you have to consider the depth also and catchment coverage also. Okay, whether that storm which you have selected, that is covering your entire catchment or not. Again, it is written, if there is any barrier between the storm and transpose location, means your storm occurred say near Pune and you want to transpose that storm 100 kilometer at some location. So between that location at Pune and that your project location, if there is any barrier where the differential height is more than 800 meter, then the storm will not be transposed. Then transpose the storm in project catchment and rotate it anti-clock or clockwise to get the maximum depth. But that rotation should be restricted to 20 degree only. You cannot rotate by 90 degree or 30 degree or 40 degree. So for maximization, your rotation should be restricted to 10 degree only. Normally we consider 20 means normally we consider 10 degree on either side, anti-clockwise or clockwise. So that will be total 20 degree. In extreme cases, you can go in one direction also up to 20 degree, but normally it should be 10 degree on either side, either clockwise, anti-clockwise. So total 20 degree. Then read the representative dew point temperature at storm location and maximum dew point temperature in the same fortnight of storm occurrence at storm location and transport location. Suppose the storm had occurred on, say, 24th July at Pune. Okay. In that case, now, when this storm occurred, say 24th July 1986, so from 1 week, for a 1 week duration, the dew point temperature in the entire area shall be calculated, and that we give the representative dew point temperature when this storm occurred at Pune. And in the same fortnight, same fortnight means from 16th July up to 31st July, we will see what is the maximum dew point temperature from the historical data that location. Okay, so that is calculated, and from that this maximum dew point data has already been published in our PMP Atlas in the form of, just like you see the ISO heights map, same way it has been published, and using if you are having the latitude, longitude, or you can take the latitude, longitude of storm location, then basically storm will be a very big one, but we consider the latitude, longitude of the eye of the storm. Okay, and based on that, you shall be eye of the storm is where the maximum rainfall depth has been recorded. Okay, so at that location, you have to see what is the historical dew point temperature in that same fortnight means every 15 days. Like in every month, there will be 2 fortnight. In January, like from January 1st to 15 January, then 16th to 31st. In September, same way, from say 1st September to 15 September, then 16 to. So total 24 ISO high. Total 24 such maps have been published, and that those are given in our PMP atlases also. From there, you can get the maximum dew point temperature data and the representative dew point temperature data of that particular storm is also given in our PMP atlases. Okay, that is a very comprehensive document, because from the meteorology point of view, whatever you can think, everything is available in these PMP atlases. Then estimate the barrier height H1 between the moisture source. Moisture source normally will be sea, suppose Bay of Bengal or Arabian Sea, and storm location. And suppose now storm occurred at Pune, then from the sea up to Pune, is there any barrier? If there is a barrier, then you have to see the differential height of that barrier. Okay? Then estimate the barrier height H1 between the moisture source and the storm location, that we call the barrier height H1. And then also calculate the barrier height H2 between the storm location. Now from Pune, you are further say transposing that storm to another location and project catchment. So from storm occurrence location up to the project catchment location, if there is any barrier, that you have to see, and you have to note down the differential height of that barrier H2. The one important thing about the barrier is that barrier, it should not be a single peak of say some 500 meter extent. No, of length. No. Barrier, we will consider the barrier if suppose a barrier, if it is extending for say 5-6 kilometer, a continuous ridge is there, because if only 500 meter a peak is there, then the storm can pass that. But if it is a continuous barrier, extending up to say 10 kilometer, 12 kilometer, which is like that continuous, then that shall be considered as a barrier. And in that barrier, you will not get the same elevation at every level. Somewhere elevation will be say 1000 meters, somewhere it will be 800 meters, somewhere it will be 900 meters. You have to consider the average elevation. Okay, consider 4 or 5 points on the Google Earth itself or whatever maps you are available, and you see, and then you take the average. What is the average? But that rich portion one. that will be considered as the barrier height. That every height what you are considering, that shall be considered the barrier height H2 or barrier height H1. It will be calculated like that. Then compute the location adjustment factor. Why this location adjustment factor? Because we are transposing our storm from one location to another location. So depending upon the difference in the dew point temperature, storm characteristic will have little bit difference. So to account for that, this location adjustment factor is applied. Then if some barrier is there, barrier height is differential height is not more than 800 meter, then for that, suppose the barrier height is 600 meter, differential height is 600 meter, then you have to apply the barrier adjustment factor. So these two factors are very important, LAF and BAF. So based on, once you have got the location adjustment factor and barrier adjustment factor, multiply both that, then you will, that is called the transposition adjustment factor, that is TAF. TAF is equal to LAF into BAF. Okay. And your SPS will be transpose depth into LAF into BAF, means transpose depth into transposition adjustment factor. That will give you SPS value. And PMP value you can get multiplying SPS value with the moisture maximization factor. What is the moisture maximization factor? Moisture maximization factor is applied in situ at the storm location. Suppose the storm I was at Pune, that at Pune only you have to apply the moisture maximization factor, and for that you require two data. One, what was the representative dew point temperature when the storm occurred, and what is the historical dew point temperature at that location during the same fortnight. So using those two data, you can, there are tables in the WMO manual, and then you can work out the what would have been the moisture depth which could were likely to get precipitated if the dew point temperature had been the maximum one. So based on that, I will show you how we are doing that. Now, I will just explain how these adjustment factors are worked out, and you should be very careful whenever you are computing the adjustment factor. It is very easy, but you have to be methodological. You have to follow, you have to go step by step, and whatever the procedure is given, you have to follow that one. So this is the same moisture source like Bay of Bengal, and storm occurred at this location, where it is written storm center, a red dot is there. Now from this location, our project catchment is somewhere here, and where in that project catchment we are going to transport, that will be the transport location. Now from moisture source up to the storm center, there is one barrier. So that barrier height, differential height, that shall be called H1. And from storm center to project location, when you are transposing, when you are moving the storm from here to that location, then you have to see if there is a barrier. To that barrier, what we are getting, that is the barrier height H2. Okay. Now, how the location adjustment factor is calculated? Like it is written in our PMP atlas, ki outstanding rain storms in a meteorologically homogeneous region surrounding a project basin are often transposed to the basin to frame PMP estimate for project basin. The transposition of rain storm necessitates application of two adjustment factor for location and barrier. So location adjustment factor, this LAF is equal to W3H1 divided by W2H1. It is same nomenclature is given in the WMO manual also. So there should not be any confusion. So whatever is given in that we have given in our PMP atlas same way. Now see, the H1 is the mean crest elevation of the barrier between, see here, mean crest elevation. Like I already told you, suppose that somewhere elevation is 1000 meters, somewhere 950 meters, somewhere 900 meters, somewhere 800 meters, then you have to take the average of that. So mean crest elevation of the barrier between the rain storm center and source of moisture with mean crest elevation higher than that of the rain storm center. If it is lower than the rainstorm center, then HOD will not be required. But if it is higher than this, suppose a rainstorm center elevation is 300 meter, but barrier height is 500 meter. This 200-meter difference is there. For that, you have to apply the correction factor. But suppose that storm center location is 400 meter, but the barrier elevation is 300 meter, then you need not to apply this barrier correction factor. Now, W2 is the precipitable water in an atmospheric column between 1000 and 300 HPA. What is 1000 HPA? 1000 HPA is the basically mean sea level. This is the pressure corresponding to mean sea level. And 300 HPA, it may be at an elevation something around say 6000 meter. Okay, so W2 is the precipitable water in atmospheric column between 1000 and 300 HPA levels corresponding to maximum persisting dew point temperature D2 on record at location of the storm in same fortnight of the month in which the rainstorm occurred. So temperature you have to remember that D1, D2, D3. D1 is the persisting dew point temperature at the storm location. D2 is the maximum persisting dew point temperature at the storm location in the same fortnight. And D3 is the maximum dew point temperature at the transpose location. So D1, D2, D3, D1 and D2 are at the storm center, at the storm location. D3 is corresponding to transpose location and in the same fortnight. Again, fortnight you have to be very careful. Suppose the storm occurred on 24 July, then the fortnight will be the second fortnight of July. So, at some other storm you are considering which occurred in the say 7th of August, then you have to consider first fortnight of the August only while computing or this maximum dew point temperature. Okay, so using this equation, LAF can be calculated. Now, barrier adjustment factor. You see, I have shown one schematic diagram also. What is this? Like you are what was showing this blue column, that is the moisture column which is going to precipitate. Now storm is occurring from say windward side, from sea side, and one barrier is there, then what will happen? And this barrier is continuous. Okay, so corresponding to its crest, mean crest elevation, rest of the like this portion, what you are seeing from here to here, this much moisture will get precipitated on the windward side. On the leeward side means after the hillock, only this much, what you are seeing through the red arrow, only this much precipitation or moisture is available which can get precipitated on the leeward side. So to account for that, this barrier correction factor is applied, and this is very important because most of the people do carry out mistakes while estimating the barrier adjustment factor. I have seen number of experts, very good experts, while I was estimating for Sardar Sarovar project, they have considered one storm, but they have not applied a barrier correction factor, but barrier was there. And when I applied that barrier correction factor, so whatever the flood they were estimated, they estimated flood of the order of 1,71,000 cubic, but I have got 1,04,000 cubic. So you can imagine around 66,000 cubic difference was there because of that barrier correction factor. So that is very important. So BAF is equal to W3H2 divided by W3H1. H1 is the height of the barrier from storm moisture source up to storm location, and H2 is the height of barrier from storm location to transpose location, and W3 is the precipitable water in the atmospheric column, again between 1000 and 300 HPA level corresponding to maximum persisting dew point temperature D3 at the transpose location. Okay, so and how you are going to calculate the average barrier, like you see here I have seen, this is the storm location, SLMC is storm location, and TL is transpose location, and then you have to just draw a line and then seeing this, considering the average mean crest level, and then from this line, how much difference is there. That way you can calculate what will be the barrier height. Now, another important correction factor, that is the moisture maximization factor. This is used to convert standard project storm into probable maximum storm. So this is MMF is equal to W2H1 divided by W1H1. तो W2 क्या है? W2 is the precipitable water in the atmospheric column between 1000 and 300 HPA corresponding to maximum persisting dew point temperature D2 on record at the location of storm, and W1 is the precipitable water in the atmospheric column between 1000 and 300 HPA level corresponding to representative persisting dew point temperature at the storm location. So this is in situ where the storm occurred. At that location, moisture maximization factor is applied, because whenever we are computing probable maximum storm, so our PMP depth, so PMP depth is always calculated. First you have to calculate the SPS depth, then multiply with moisture maximization factor. That will give you the value of PMP. Or you can directly calculate key, if you multiply moisture maximization factor with LAF and BAF, then you will get the moisture adjustment factor, and your PMP will be transpose depth into MAF. But I will again say you should follow this step. First you calculate SPS. SPS is equal to transpose depth into LAF into BAF. Then you calculate PMP equal to SPS into MMF. If you are directly calculating using MMF, then in certain conditions you may get PMP value less than the SPS, and that will be because of the some computational error. So always follow basic step. First calculate SPS using transpose depth into LAF into BF formula. Then you calculate the PMP value by multiplying the SPS with MMF, because PMP can be equal to the SPS or more. Normally PMP will be 20% or 25% depending upon the moisture, or 7% if near the coast, it may be 7% more than the SPS, but in the inland area it may be even 40% to 45% more than the SPS. Okay, but PMP value can never be less than the SPS. This basic fundamental you should always remember. Now, this was all about the storm, how we are considering, how we are selecting the storm, and how we are transposing, and then after transposition, how we are calculating the SPS depth, standard project storm, that is used for the SPF calculation, or PMP depth. Okay, by applying the suitable correction factor. Now, let us discuss about the basin response characteristics, that is the unit hydrograph. So what is the unit hydrograph? That is the response of the catchment for 1 unit of rainfall excess. That unit may be 1 centimeter, 1 inch or 1 millimeter. It hardly matters. You can consider any unit. But if you are considering here 1 centimeter, then your rainfall should also be in centimeter. If you are considering here 1 millimeter, then your rainfall should also be in millimeter, because then you are, once you have made this consider the unit here, then the same unit you have to take there also, because if you are have considered here 1 centimeter, you have made the 1 centimeter 1 centimeter unit hydrograph, but your rainfall is in millimeter, and you are multiplying this 1 centimeter unit hydrograph ordinance with the millimeter of rainfall, then you are committing a big mistake. You are in that case, what you have to do, convert this 1 centimeter. You can calculate 1 centimeter, like in our flood estimation reports. Mostly we are calculating the unit hydrograph corresponding to 1 centimeter rainfall excess. Calculating, make the unit hydrograph, then divide all the ordinates by 10. That will give you the unit hydrograph for 1 millimeter rainfall excess. Very simple, linear. Okay, and then once you got the for 1 millimeter and your rainfall is also in millimeter, because if you are using HMS, then there the unit shall be used millimeter or inch. Okay, so now Yes, I think there was one pop-up ki how this maximum rainfall precipitable column, it is calculated based on the table provided in the WMO manual. In WMO manual, you can get, and even in the PMP Atlas, also in our A3 size. Our PMP Atlases are given in A2 and A4 and A3 size. In A3 size, in last few pages, you will see chart is given to compute to this precipitable column of water. Okay. There was one pop-up, somebody was asking about that. So a unit hydrograph thus has a duration, and that duration represents the duration of excess precipitation that generates the unit hydrograph. Like, suppose I am telling you ki this is the unit hydrograph of 1 centimeter rainfall excess occurred in 1 hour duration. Then the duration of unit hydrograph is 1 hour. If I am telling 1 centimeter rainfall excess occurred over a period of 2 hours, then that will be the unit hydrograph of 2 hour duration. So like in your graduation course also, you must have read how to convert 1 hour unit hydrograph to 2 hour unit hydrograph or 4 hour unit hydrograph, and how to convert a 4 hour unit hydrograph into 1 hour unit hydrograph or 2. So like as you different methods are there. So I'm not going to explain because that is the basic fundamental change which you can see in that any textbook. Only thing what I am telling you, you should be consistent with the unit and duration. Okay. Like, why duration is important? Suppose you have made with 2 hour unit hydrograph. Then your rainfall hydrograph ordinate should also be at 2 hours. Only then you can carry out the convolution. You cannot take here your unit hydrograph duration is 2 hours and then you are have made the storm hydrograph at every 1 hour. That is fundamentally incorrect. In that case, if 1 hour unit hydrograph is there, then you can take the hourly distribution coefficient, and using that hourly distribution coefficient, you can go for the convolution. Now, derivation of unit hydrograph. The unit hydrograph is best derived from the observed hydrograph resulting from a star which fulfills the 2 basic conditions. What are those conditions? Number 1, the rainfall is more or less uniformly distributed over the basin and has a reasonably uniform intensity. Such a hydrograph will generally form a simile and short peak. If that such type of your observation is there, then using Collins method, and all those methods are given in the textbook, you can work out the unit hydrograph for that catchment. Another way, if you are having at that data, you are having concurrent rainfall and discharge observation, then using Nash and Clark method also you can derive the unit hydrograph from the observed data. If in the case, if such hydrograph is not available, then the unit hydrograph has to be derived from the analysis of an observed complex event. In complex event also, if you are having a complex event, then the Nash model is a good alternative. Using that complex event, you can make the unit hydrograph. When observed discharge and rainfall data at certain interval is not available, then we can make this synthetic unit hydrograph using the basin characteristics like longest flow path, catchment area, basin centroid, basin centroidal longest flow path. Using those, there are Schreider method and flood estimation report. Okay. So Santa Water Commission has published number of flood estimation reports of different like FER 2A for North Brahmaputra, FER 7, FER 3A, 3B, lot of flood estimation reports of different regions of the country are available. So using those flood estimation reports, because if you are using you are doing this estimating the flood, then better if you are not having the observed data, then you can use the flood estimation reports of CWC. Don't use Schreider method, because these flood estimation reports, the fundamental is same as Schreider method, but here whatever the coefficients has been worked out for the different equation, that is, you should remember, that is based on a number of observed data or different bridge sites, and It took a lot of effort to prepare those flood estimation reports because that data was collected in association with the Ministry of Railways and Ministry of Surface Transport at a number of bridge locations. This uh, hydrograph or hourly gauge data and discharge data were collected, and in the project catchment, number of rain gauge stations were also installed. A lot of data was collected for fairly long period, 10 or 15 years. And using that observed data, these synthetic unit hydrograph or flood estimation report. So it is not the complete, yes, equations are empirical, but based on the observed data, because a number of times I have seen the people from academia, they are more they ask me such question, oh, this flood estimation report synthetic. So for those people, if anybody is attending from academia, then they should understand that those equations have been worked out using the observed concurrent observed rainfall and runoff records. Now, design flood hydrograph. For estimating the design flood hydrograph, the effective rainfall increments of each belt are rearranged with respect to ordinate of UH such that the maximum rainfall is placed against the maximum UG ordinate. Next lower value of effective rainfall against the next lower value of SUG ordinate, and so on. So that is called the critical sequencing. Once you have got the unit hydrograph, and then you have got the storm hydrograph. Then from storm hydrograph, just deduct the losses. You will get the effective storm hydrograph, and then go for the critical sequencing, like arranging the maximum rainfall against the maximum UG ordinate, second maximum against the second maximum of the UG ordinate. That is called. And once you have got the sequence, that sequencing reverse. That is basically optimization technique. The effective rainfall arrangements obtained are then reversed to obtain the critical sequence, the sum of the product of UG ordinates and critically sequenced effective hourly rainfall gives the total surface runoff, to which you have to add the base flow to get the design fluid hydrograph. This is the lumped versus quasi-distributed model. Like if you are considering the entire catchment a single unit, then you're like this is your lumped. Here you are seeing only one outlet, but here what you are seeing number of sub-catchments have been made, SB1, SB2, SB3, SB4, and this system will work lumped plus channel routing as a lumped and channel routing system. And by you will get, like for this sub-basin, you will get the lumped rainfall at this location, okay, that is junction. For this basin, you will get your lump response at this junction. So what will happen? The lump response from junction 1 will reach at junction 2 by channel routing through reach R1, and the routed response at junction 2 shall be added to the lump response of SB2 at this location. The resulting flood hydrograph that shall be routed through reach R2 to get its outflow hydrograph at junction 3, and there this SB3 response will be added. Then the resulting one at junction 3 that shall be routed through reach R3 to get to reach there, and also SB4 response also received at junction 4 shall be channel routed to reach at MBS, and then SB5 lump response will also go to MBS. All the three will be added, then you will get the flood hydrograph at project location. So that is the difference. But here directly you have to go for you have got the unit hydrograph and you have got this hydrograph, and by convolution you are directly getting the flood response and the project location. So this is the difference between the lumped and quasi-distributed model. Now let us explain. I will show you, because I am not going to discuss the lumped response, single lumped response, single catchment. I will show you because for single catchment, you need not to go for the storm transposition. In most of the cases, you can take the PMP value corresponding to your catchment area, areal PMP value from our PMP atlas in that table is given. But for the large catchment, transposition is required. And for that transposition, you have to worked out the, suppose you have made 3 or 4 subcatchment, so for each subcatchment, you have to estimate the depth of the rainfall. So I will explain this through a case study of Gundal Kamma project. This is a project situated in Andhra Pradesh. It is constructed across Gundal Kamma River in Prakasam district. Its location is given 15° 40' north and 76° 46" east. FRL is at elevation 24.38. Live storage is 55.8 MCM. Grass storage is 109 MCM. Because grass storage is more than 60 MCM, then the project qualifies for your probable maximum flood (PMF). Catchment area is around 8,000 square kilometer, that is 7982. This is the location of the project. What you are seeing, this is the dam location, and what this is spillway. So it is a district project. Let us see its design flood review. So as per criteria, if any of this criteria is like grass storage and hydraulic head, so using this criteria as per given in IS 112223/1985, you have to select the appropriate inflow design flood. It may be 100-year standard project flood or probable maximum flood, but here it is important to again mention it. If suppose a project is having its hydraulic head is only say 20 meter, but if grass storage is 90 MCM, then that shall be, means either of any criteria, either hydraulic head or grass storage is met. Based on that, this project shall be qualified for the probable maximum flood. Okay, so if any of this criteria is meeting, then you have to consider the appropriate design flood. So this is the catchment area map. Project location is here. So we have made 3 subcatchment: SB1, SB2, SB3. Okay. So if you see this SB1, here the catchment area is 997, SB2 3584, SB3 3401. You can make 5 subcatchment also, 10 subcatchments also, but ultimately your design flood value will have of the same order. Your maximum difference may be of the order of 0.5% or 0.2%. So too many subcatchments are not required. So that also, because somebody was asking how many subcatchments. So depending upon the seeing the shape of the unit hydrograph, you can decide, but normally for around 1,000 or 200 square kilometer, even 3,000, like here up to 5, because this is a plain area, so up to 5,000 square kilometer we can go for a single catchment, but 5,000 is still seems to be high, so we have considered some 3,000 or 3,500, and then for one subcatchment, depending on, because here the river was coming like that, so one subcatchment has been from here, so 3 subcatchments we have made. And for each, when you are making the subcatchment, then the longest flow path and centroidal longest flow path and equivalent steep slope has to be calculated for each of the, like you see here. If you consider SB3, so here the main river is coming like this one, but its longest flow path, you see, it is starting from here, because one very renowned hydrologist, he was PhD and he committed such mistake. What he was taking the longest flow path from here to here. So you have to be very careful. The longest flow path will be longest flow path of that subcatchment only. Okay, not this main river, longest flow path of that subcatchment. If you are making the subcatchment, so that should be computed very carefully. And then these are the centroid locations of each subcatchment. From that centroid, you just project one perpendicular on the longest flow path where it will cut from that location up to outlet of that project. That will give you the length of the centroidal longest flow path. And then equivalent stream slope in our flood estimation report, how equivalent stream slope should be calculated. For that formula is given. So using that, you can work out the equivalent stream slope. So for each of the sub-basin, we have calculated the longest catchment area, longest flow path, centroidal longest flow path, and equivalent stream slope. Then Using those parameters and flood estimation report, because here the observed concurrent rainfall data was not, so we use the flood estimation report, and that flood estimation report name for that zone is subzone is for ABC, that is applicable for Andhra Pradesh, particular that basin. So for you have what you are seeing, this is the unit hydrograph of subbasin 1. This is red color is the unit hydrograph of subbasin 2, and this blue color is the unit hydrograph of subbasin 3. Okay, so this Gundal-Kamma project lies in Kaveri Basin. For that, we are having PMP Atlas published by CWC in May 2015. From the PMP Atlas, what we have found, this project qualifies because here the seeing the catchment area and all those time base of the unit hydrograph. This project qualifies 2-day storm for design rainfall depth computation. Further, from the PMP Atlas, what we found, 2-day storm for the Gundal-Kamma project catchment is the storm dated 13 to 14 May 1979 with the eye of storm at Satanjutal and recorded 2-day peak as 525 millimeter at its eye location. This Satanjutal rainfall, its 2-day peak 525 millimeter at its eye. The corresponding, and again, if you are considering the 2-day storm, then from this for the same storm you have to see whether 1-day storm is available or not. If not available, then you have to consider the 2-day storm only, and then using the 2-day distribution coefficient, you have to work out this 48-hour distribution coefficient, what will be the rainfall date in 24 hours. But if the storm is available, 1-day storm is available, then you should consider that 1-day storm. So here, in most of the cases, you will consider you will get 1-day, 2-day, and 3-day storm of the same storm occurrences. So, corresponding 1-day storm, it was of 13th May 1979. It may be 13th May or 14th May. So whichever day is maximum, that shall be considered a 1-day storm. It has already been accounted for while giving the 1-day storm or 2-day storm name in our PMP Atlas. You need not to worry about that, because based on the analysis, whether a 13th May storm shall be considered of 1 day or 14th May. So here it has been 13th May storm. So that is given. So here the recorded 1-day peak is 430 millimeter. So you see 430 millimeter occurred in 1 day and 525 millimeter occurred in 2 days. Now, based on the critical transposition of the storm isohydrates, because for 1 day also and 2 day also, both are to be transposed. The transposed depth for each subcatchment has been computed. The procedure I have already explained you, the same procedure we are following. The transposed depth has been multiplied with transposition adjustment factor, that is TAF, and moisture adjustment factor to get the 1-day and 2-day PMP for the each subcatchment. The rainfall persisting dew point temperature normalized at 1000 HPA was 24.8 degrees centigrade. The maximum persisting dew point temperature in the first fortnight of the May at the Kanigiri normalized at 1000 HPA is 28.4. Why I am writing normalize? Why? Because suppose 1000 HPA means mean sea level. I have already explained to you. Suppose this dew point temperature was at a location, we projected dew point at a location where the observatory was, say, at 300 meter elevation or 500. So that temperature has to be adjusted corresponding to mean sea level. Only then you can utilize. So you should be very careful. Ki suppose in our PMP Atlas that has already been accounted for. But for a new storm, if you are analyzing and your observatory was, say, at 500 meter elevation, so whatever the dew point data you have got, you correct that corresponding to 1000 HPA, and for that also chart is given in the PMP Atlas as well as WMO manual. The maximum persisting dew point temperature in the first fortnight of May at transposed location normalized to 1000 HPA is 27.1 degree. The storm location is at elevation 100 meter. The barrier elevation between storm location and transposed location is 700 meter. So all these data we have used, and then we have worked out the what you are seeing. This is the 13th to 14th May 1979. This is the original storm. It's ISO high and its eye is here. Now, just compare both. Here what you're seeing, eye is here. Now, for maximization, if you see the wind transport, then the eye is coming here. And corresponding to this location, we have got the maximum depth. So you have to put the storm or eye at different locations of the project catchment, and for each location generally we take 4 or 5 trials, and then we see at what location in 3 or 4 or 5 trials you will get the location where you will get which location is giving the maximum depth. So that trial you have to carry out while transposition. So corresponding to the maximum depth location, this is the isoidal pattern. This is the location where we have transposed. Now, if you see here, what is the barrier? Because if you see here, the from this moisture source is this. I have just Google Earth itself, you can see. And here the location is 114 meter. So there is no barrier between storm location, moisture source and storm location. So average 100 meter or 14 meter, whatever we have considered, like we have considered here, this 100 meter storm location is at elevation and there is no barrier. So H1 height shall be taken as 100 meter itself here. The H1 will be 100 meter. Okay. Now, because there is no barrier. Now, so barrier H1. In this two, if you are seeing here 758, something like that. And this is continuous ridge. So from storm location up to project where we have got the maximum depth corresponding to which location. So there we are getting one barrier also. So that barrier elevation also we have noted H2, and then 1 day and 2 day final transposition where we are getting the maximum depth isoidal pattern you are seeing here. And how we have calculated, like T1 means persisting dew point temperature was 24.8. It is given in the PMP atlas for that storm. And D2 means maximum dew point temperature in the same fortnight when the storm occurred at Kanigiri location, that is 28.4 degrees centigrade. And at transpose Gundalkamma project location where we have put the eye at that location, the maximum persisting dew point maximum dew point temperature, the projected dew point temperature in the same fortnight is 27.1 degrees centigrade. So using this WMO table, which is given in our PMP atlas also, we have got the WN H1 as 77.2 millimeter. This is the equivalent moisture column which is likely to precipitate, which will precipitate W2 H1 and 105.4 millimeter. W3H1 94.2 millimeter, W3H2 80.4 millimeter, and height of barrier H1 is 100 meter. Height of barrier H2 we have considered average height. This is the mean height. Okay, 700 meter. So using this we have found the LAF at 0.89, this barrier adjustment factor 0.85, and moisture maximization factor is equal to 1.36. It means your SPS is going to be 36% more than your PMP is going to be 36% more than the SPS. So for each sub-basin, SB1, catchment area this, transpose depth 1 day, 2 day, SPS value 1 day, 2 day, PMP value. So for each sub-catchment, we have estimated the SPS and PMP value. Okay. Now, once we have got, then hourly distribution coefficient also you will get in the PMP atlas. So distribution coefficient for 24-hour and spell, and then we have considered normalized distribution coefficient for 12-hour well. Why we are considering 12-hour well? In India, especially, what we have found after analyzing all these most around 100 of rainfall data, he generally in 1 day, in 1 12-hour, maybe in afternoon or any time in 12 hours, that rainfall is around 65 to 70% of the 24-hour rainfall, because this bell condition is not applicable for European countries and other countries. It is applicable for Indian continent only, because India is the only country which is having a fixed storm track and monsoon pattern, and here the rainfall characteristics are of our country. So that's why this bell theory has been evolved, because 70% rainfall is occurring in 12 hours. So that's why two bells are being considered for each day, and each bell will be up 12-hour, 12-hour. Like what you are seeing from this distribution, that this 12-hour rainfall is about 73.4% of the 24-hour rainfall. So to get the normalized distribution, now first what you have got the 24-hour depth. So then what will be 12-hour depth? That say your 24-hour depth is 200 millimeter. So what will be the 12-hour depth? That will be 0.734 into 200. That will give you your 12-hour depth. Now, once you have got the 12-hour depth, then you have to use normalized distribution coefficient. How we are getting? Now divide each ordinate, each value with 0.734. You will get the value of normalized distribution coefficient, because at 12 hour it should be 100%. These are the loss rate and base flow. This is also given in our flood estimation report. So here we have considered the design loss rate of around 5 millimeter per hour. Base flow is about formula is given 0.536 divided by catchment area to the power 0.5. So using these equations, we have estimated the base flow also. Base flow computation, like SB1, it is coming around 14.44, SB2 26.58, SB3 25.93. So once we have got all these things, now for rainfall depth for each 12-hour bell that we have calculated, like first you have to make table like this one. 1 day PMP this one, 2 day PMP this one, okay, and 3 day then 1 day PMP, that whichever the maximum 189.80. Second day PMP will be 220.69 by 189.80 we have got here. So for each day we have calculated. Then 24 hour, because if you are considering 2 days, then your clock hour correction is not required. But still, just for the arrangement of the bell, we have to see. Suppose I want to put B3 and B1 together. So for that, their sum should not be more than this 24-hour max. So for that, we have calculated 24-hour max also. That will be 15%. You multiply this value 1 day maximum with our 1 day PMP with 1.15, and then you will get this 24-hour rainfall depth. Then first day PMP, first bell, second bell PMP, 12-hour bells are there. So like that, for each bell we have calculated. And since sum of the B1 and B2 is less than the 24-hour rainfall in two subcatchments, hence bell sequence used for correlation is B2, B1, B3, B4. So once you have got, then like I have already explained in my previous lecture also, this is the distribution coefficient for each bell. Normalized distribution coefficient is also given here. Using normalized distribution coefficient. Yes, somebody want to know about the base flow? What is the confusion there? You have to calculate simply using this formula. So cumulative rainfall depth you have got for each bell. After that, you calculate the incremental, means like here first is 39.29, then second from first hour to second hour, how much rainfall? That will be 66.24 minus 39.29. So like that you have to calculate. Then you have to subtract losses. After subtracting the losses, if any negative value, then that you have to make 0, 0, 0. It means zero runoff will be generated from that hour of rainfall. So that we have got the effective rainfall depth for each bell, and then for each bell we have to go for SB1, SB2, SB3. This computation will be like this same. Then using any of the, because you have need not to go for the critical sequencing for each subcatchment. Earlier people used to do, but it hardly matters. Better ye out of SB, SB2, SB3, we have critical sequencing we have carried out with respect to UH of one subcatchment. Like we have considered the UH with of SB2, that is central also, and its UH was also giving the maximum peak. So with respect to that, we have to go for we have done the critical sequencing of the rainfall of that particular subcatchment using the UH of SB2. And then once you have done the critical sequencing, then the reverse critical sequencing has to be convoluted with the unit hydrograph of that subcatchment, not of SB2. For SB2, you will use SB2 UH. For SB1, you will use the SB1 UH. For SB3, you will use SB3 UH. Okay. So critical sequencing for SB1, SB2, SB3 that we have carried out, but critical sequencing we have carried out with the UH of SB2 only. But convolution we will do. This critical sequencing rainfall shall be convoluted with the UH of that subbasin only. Now, this is the HMS model. What you are seeing, this is the SB1. Its lumped response is coming at junction 1. From junction 1 to junction 2, we have made one routing reach R1. This at SB3, lumped response is coming at junction 2. And SB3, no evaporation losses are considered here. Losses means we have already considered the losses. Evaporation losses you have to consider in the water availability analysis, not in the design flood. Okay. Somebody was asking that question. I have just replied that one. So SB2 lump response is coming junction 2. SB3 lump response is coming at directly at the project. So how the system is going to be at? SB1 lump response we have collected at junction 1. From there it has been routed through reach R1 to reach at junction 2. At SB2 response is also coming at junction 2. So both has been added, and then the total flood hydrograph has been routed through reach R2 to get the routed flood hydrograph at Gundalkamma, and that will be added with the SB3 lump response. That will give you the resulting hydrograph, will give you the design flood or flood hydrograph, design flood hydrograph Gundalkamma. Now, when you are going for the routings, like here we have used the most of the time we are using the Muskingum routing. You can go for the hydrodynamic routing also, but for that you need the river cross section. But Muskingum routing also, if you are sticking to the stability criteria, it is going to give around result about 95 to 96% accuracy, and that in comparison to the hydrodynamic routing. And this is also very cheap also, because you need not to go for any cross section survey, etc. So, but only thing that is important key, because here see the routing reach is 72 kilometers. So I cannot go in single step routing, because in Muskingum criteria what you have seen ki delta T means your flood hydrograph coordinates. Here our flood hydrograph coordinates are at every 1 hour, because you have seen the here we have made the 1 centimeter 1 hour duration unit hydrograph, and our flood this hydrograph coordinates are also at every 1 hour. So our delta T is 1 hour. So delta T should be greater than 2 kx, where k is equal, k is the travel time to the river reach, and x is weighing parameter. Its value normally for the open this rivers you can take from between 0.15 to 0.25. Okay, so normally you can consider for 0.20 to 0.25. Okay, so and k is the, so here k is around 12 hours, and x is equal to 0.2 number of, because delta T is 1 hour. To just to for the stability of the routing criteria, while routing you have to make a number of sub reaches. Only in the model you have to give number of sub reaches, like we have given 5 here, you have given 6 here. So your routing algorithm is going to be stable. Otherwise, if you are not following that one, then we will not get a proper routing result, and your estimated flood will be less in comparison to the actual correct flood. So these are the model regions. Like for SB3, this is the lumped response, and this is the SB1 lumped response. This is the SB2 lumped response, and this is the routed flood hydrograph. This is from the reach R1. You have seen the peak here, and after routing, when it is going to junction from R1, here you are seeing the peak maybe of the order of 2200 cubic, but when it is reaching at junction 2, after traveling to a reach of 72 kilometers, then it is getting attenuated by 700 cubic, around 1500 cubic. Then again from junction 2 whatever the net flood hydrograph you have routed here, it is something around, say, around 13,000 cubic, and here it is reaching 10,000 cubic, around 3,000 cubic at elevation has taken place. And once you have reached at that junction, so here the routed reach R2 response plus SB3 lumped response, both are shown here. One is SB3, this is the SB3 lumped response, and this is the R2 reach routed flood hydrograph. Both are added, and in adding, it will be in model, it will be added. But if you are doing on Excel, the people try to match peak to peak. I think that is the foolish thing what the people are doing. You should never go for the peak to peak matching the natural condition, because the travel time is only for lagging the peak. Okay, that is the natural phenomena. Don't try to play with the natural phenomena. Whatever natural phenomena is happening, you should consider that one. So never do the peak to peak matching. So it is automatically like here, when the peak of this lump response is coming, at that time is routed flood hydrograph coordinate is this, so both will be added, and so the net will be this one, and here the peak we are getting corresponding to that. So that way, so here what we have found is that the revised PMF is of the order of more than 16,000 cubic. So with that, this is the final flood hydrograph, and it is something around 1600, 500, 600 cubic. So with that, that way we can calculate the device design flood for any project location. So with this, I am finishing my lecture here. Thank you very much. Now, if you are having any question, then you are welcome to ask those questions. That's up.
Sir, the session was really very enriching, and this was a special session on this case studies of hydrological review as per request from the participants, and this was delivered very in awesome way. Sir, sir, queries are there in the chat box. Sir, queries are there in the chat box.
Okay.
Can we take one by one all the queries?
Yes. Okay.
Sir, if you stop your presentation,
just एक बार इधर आना. हाँ. Just I will call it. I take कर दूँ.
एक बार सर ये अगर स्टॉप कर लें तो चैट बॉक्स आपको दिख जाएगा.
एक मिनट. Okay. Yes. First query is what is the minimum number of rain events required for estimating and updating the hourly distribution coefficient for taking into account the impact of climate change in the present hydrological study? So we consider first, yes, its answer is like that. We consider first, we take a threshold value that way we say 200 millimeter in one day, 200 millimeter. Okay. So for corresponding 200 millimeter, we will see all the records in the last 5 or 6 years. Okay. So normally, because we are taking the average of different rain gauge stations, so at least 5 or 6 years records, that will give you the trend, actual trend, because from one stop you cannot get the trend. So maybe 20, 25 or how many rain gauge stations data you are getting, but for the rainfall of more than 200 millimeter and latest 5-6 years data, that will give you a good idea of how the rainfall pattern is occurring nowadays. Then how do we know the orientation of the storm from the isohydral map? That is very easy. Just from you see the direction, how this layout of the isohydral is there. So just seeing the layout, you draw a line, you will see the orientation. Then the 800 constraint is for H1 or H2. That is for H2. This is the barrier between the storm location and the transpose location. Then each change in MMF heading to increase the PMF values. Yes, certainly, if the change in MMF is going to change the PMF value. Then how the maximum precipitation water column is changing over the years. That is being up. I think that has not been updated by WMO earlier, but I think whatever given in the recent their manual, that is the latest one. Okay, so you can use that one because it is not going to change very fast. Okay, so at this last 20 or 30 years, a lot of data has been analyzed and that average phenomena has been captured in that. Then apart from the synthetic unit hydrograph from FER, where site-specific UHG has been derived, whether site-specific of the project under whose design flood has been devised by CWC for drip. I think for drip, we have considered the SUH only for certain projects where the actual data, especially in some projects of Bhakra Beach Management Board, where the actual observed data was available, their unit hydrograph has been derived using that data. Then many of the states are implementing agencies of NHP project and most of the dams are 40 to 50 years old. The dam owners may be having the latest concurrent rainfall runoff records. Whether this data has been used for deriving project specific unit hydrograph, they are having the mostly because we need the unit height for making the unit hydrograph. I have already told you, you need the flood hydrograph as well as the rainfall data, and that rainfall data should be the catchment representative. And I think now so many under NHP, lot of rain gauge stations have been installed, and if the data is available with the project authorities, then certainly that unit hydrograph should be made using that rainfall data. Okay, then it is that I have already material, yes, that will be shared by the NWA. There are many projects in same river basin. How the consistency of reviewed PMF of project will be maintained? It is to be ensured by central agency. Yes, we are ensuring that. We are ensuring that. Thank you, sir, for a wonderful presentation. Sir, there is a question that while considering the semi-distributed model for classified data catchment, say for lower Ganga catchment, how do we account for K and X, or rather where for consideration of rainfall extreme event, there is no classified data. Even in Ganga basin also the flood peak data is unclassified, first thing. And K and X, yes, that is based on the for K and X. Best thing you can get the you can ask our flood forecasting people, because from base station up to forecast station, what is the lead forecast time, that gives a very good idea about the K value. Okay, or other important thing, using the DEM in the basically in some of the terrains, if now DMs are available, and though suppose your flood peak is of the order of say 8,000 cubic, so take 75% of that, something like, because ultimately in the high very high flood water will go beyond the banks of the river, so that flow will be wave will be of dynamic wave nature. But in the Muskingum method, this K has been calculated considering the kinematic wave phenomena when the water is confined or flood is confined within the banks of the river, but in actuality it is not going to happen. So that's why you should estimate the K either getting our from data travel time data from our base station up to forecast station, or you can take the cross sections of the river from DM, and suppose your lumped response is 10,000 cubic, then take the 75% of that, around 7,500 cubic, and then you see how much velocity you are getting. With using that average velocity, you can calculate the K value. What will be the travel time for say 70 kilometers is that is also one of the way. I do like that. Can PMP value be adopted directly from the summary table given in the IMD? Yes. There is no doubt in that, given ki even up to 2,000 square kilometer to 3,000 square kilometer, you can take the directly those values. But for very large catchments, you have to go for the transposition and other study. If the catchment is 4,000, if we estimate the design storm by single catchment, yes, you can estimate for the same area. If you estimate the design storm multi, then there will be any difference, very little difference, 1% or 0.5%. We have already published one paper in this regard, because now a lot of confusion was there. So for the same catchment, we have considered single catchment. It was something around 5,000 square kilometer. So we have considered single catchment, we have considered 3 sub catchment, we have considered 7 catchments. From all that we have got, but if the catchment area is very large where the breaking is required, then there will be a difference. But for those catchments where this applicability of unit hydrograph theory, that is applicable up to 5,000 square kilometer, that is for the plain terrain. In hilly terrain, even for 1,000 is, suppose catchment area is like this, it is at some location or catchment area is 5,000 square kilometer, but the catchment is very equivalent, steep slope is very steep, say of the order of 80 meter per kilometer, then perhaps you have to make a smaller catchments of 500 square kilometer only. Base flow is considered 0.05 cubic into catchment. Yes, very right. In number of FER, that is 0.05 cubic, but in certain FER's formula is given. So whatever is given in the FER using that formula or this criteria, you can calculate the. But in our presentation, yes, in my presentation, in FER 4ABC, that formula is given. It is not given 0.05 cubic. So that's why we have considered that one. Then apart from the synthetic UHG FER, the site specific UHG has been derived for that I have already applied. Okay, so I have whatever is there given in this, I have replied all the questions of the chat box.
Yes, sir, you have answered, sir, all the questions. So participants can take advantage. Sir is still here. If you want to ask any questions, sir can answer. So from participants side, anybody interested to ask any questions?
Yeah, and while asking your question, just you can switch on your video also.
Yes. Please. So I request participants side, because this opportunity will not get very frequently, because we are not going to repeat it so frequently. So from participants side, if they have to take advantage of this webinar series, so sir is still here. If no questions, anybody? No question. So I think, sir, all the questions have been covered in the chat box only, and now with this we can conclude the session. Sir, I'm really very thankful to you, because sparing time again. Again and again is not so easy. We got this opportunity from your side. You have spared your valuable time, and really NWA is very thankful to you. And in the future also, we'll hope that your guidance will be provided to us. This webinar series are really containing all the topics, and participants, I think they are getting benefited of more benefited from this webinar series. And in this way, my sincere thanks to all the participants also who have participated in this webinar series. And just to announcement, next topic is the early warning system in hydro projects, and that will be delivered by the one expert from NHPC who have installed this early warning system in this in the project. So with this I conclude this session, and thank you all. Thank you, sir. Thank you very much.
Okay, thanks to everybody. Thank you.
Yes, sir. Yes, sir. And we were just, somebody is asking that PPT and recording. So we always provide presentation in our Moodle. NWA e-learning platform is there, that is Moodle. And we have already given all the details how to log in that Moodle platform. And there, all the topics we have covered till date. And all topics of the webinar series are put up this on that platform. Anytime, even after attending this session, anytime they can access this video also and that presentation also. So that I want to clear it. So with this, I conclude the session. Thank you very much.
Thank you, thank you, thank you.